This report investigates the technological development and operation of DC motors alongside a comparative analysis of AC/DC generators and photocells. In Part A, it covers the motor effect, traces the historical development of DC motors, examines their functional principles, and discusses their applications, culminating in a detailed investigation plan and a final model with its construction process. Part B presents a data-driven evaluation, contrasting AC/DC generators with photocells to evaluate the features, positive and negative impacts on society, and a judgment on energy production. Together, these two sections offer a cohesive overview and evaluation of electromagnetic devices from theory to practical implementation. The motor effect is where a current carrying conductor placed in an external magnetic field experiences an electromotive force. This force results from the interaction between the magnetic field created by the movement of negatively charged electrons in the wire and the external magnetic field created by the stator-magnets. According to the Lorentz force law, for a force on a current carrying conductor placed in an external magnetic field, the magnitude of the force is given by F equals ILB sine theta, where I is the current through the conductor measured in amperes, L is the length of the conductor within the magnetic field measured in meters, B is the strength of the magnetic field measured in Tesla, and theta is the angle between the direction of the current and the magnetic field measured in degrees. The angle is always perpendicular at 90 degrees to both the direction of the current and the magnetic field, with its direction determined by Fleming's left-hand rule. The motor effect underpins the operation of electric motors, as the force generated on different segments of a current loop are used to produce rotational motion, thereby converting electrical energy into mechanical work. In 1821, Michael Faraday discovered that a current carrying conductor in a magnetic field experiences a force, establishing the fundamental principle of the motor effect and demonstrating that electricity and magnetism interact to produce motion. Building on Faraday's work, William Sturgeon and Thomas Davenport developed early DC motors that used basic commutators and brushes to periodically reverse the current, allowing for continuous rotation. In the 1870s, Belgian engineer Zenobia Gramme introduced a Gramme ring motor featuring a continuous toroidal armature and an improved commutation system. This innovation increased efficiency and torque, making it the first commercially viable DC motor. During the 1880s, Frank J. Sprague advanced DC motor technology with robust designs and refined commutator and armature techniques, leading to motors that provided consistent torque and reliable performance for streetcars and industrial machinery. A DC motor converts direct electrical energy into mechanical energy through electromagnetic interaction. When a DC voltage is applied, direct current flows through the motor's armature, a coil of wire, generating its own magnetic field. This field interacts with the external magnetic field produced by the stator, resulting in a force on the armature. The armature is arranged on a rotor, with field windings positioned around a central axis. According to the Lorentz force law for motors, each segment of the conductor experiences a force as per the formula F equals ILB sine theta. The combined forces on all segments produce a net torque that rotates the armature. A key component in a DC motor is the commutator, a segmented switch attached to the rotor. As the armature rotates, the commutator, together with stationary brushes, reverses the current direction in the windings at the right moment. This periodic reversal ensures that the torque remains in the same direction, allowing continuous and smooth rotation. By optimizing the design of the armature, stator, and commutator, DC motors efficiently convert electrical energy into rotational mechanical work. This controlled motion, which is adjustable by varying the current or voltage, makes DC motors ideal for a wide range of applications. DC motors power conveyor belts, machine tools, and robotics due to the superior speed and torque control, enabling precise and efficient automated processes. DC motors deliver reliable propulsion with high starting torque in electrical vehicles, trains, scooters, and forklifts, ensuring smooth and controllable operation. DC motors drive appliances such as vacuum cleaners, power tools, and fans. Their efficient low-voltage performance makes them ideal for portable, battery-operated devices. Valued for their simplicity and precision, DC motors enable accurate motion in robotic arms, drones, and instruments, often working with sensors and microcontrollers for real-time control. They are also used in medical devices and renewable energy systems, where their robust performance and adaptability provide efficient, controllable rotational motion. The materials needed to build a sturdy, functional, at-home DC motor are the following. 1 large elongated rectangular sheet of aluminium foil, 1 insulated copper wire equal to or greater than 2 meters, 2 rigid copper wires, 1 set of 2 strong magnets, 1 sheet of sandpaper, 1 pencil, 1 rectangular piece of styrofoam, 1 large rectangular flat piece of wood, 30 centimeters by 40 centimeters, 2 small rectangular thick pieces of wood, 5 centimeters by 6 centimeters by 2 centimeters, 1 multimeter, 1 power supply set to DC and 10 to 12 volts, 1 positive and 1 negative power supply wires, 12 steel screws, 2 electrically conductive copper/brass screws, 4 ankle brackets, 2 regular and 2 slotted, 1 screwdriver/power drill, 1 pair of scissors, 1 roll of sticky tape, and 1 roll of duct tape. Start by sharpening both ends of a pencil and piercing a piece of styrofoam a quarter of the way down. This styrofoam serves as the base for your copper wire coil. Sand down one end of the copper wire and begin coiling it around each end of the styrofoam to form 2 neat loops. Make sure both ends of the wire extend equally and are stripped bare. Finally, use a multimeter to test for electrical conductivity. If it doesn't beep, send the ends further until it does. Cut 2 small aluminium foil rectangles and wrap each tightly around the bare ends of the copper wire, twisting to secure them. Adjust the wire ends to be horizontal when the copper wire coil is horizontal and tape them in place at the base of the styrofoam. Then, cut and fold 2 longer aluminium foil strips to act as contact pads. These are taped along the pencil near each copper wire end, but without wrapping them around. Make sure there's enough exposed foil and test again with a multimeter for conductivity. Now set the pencil armature aside and start building the stator base. Use a rectangular wooden board as your base, then attach 2 smaller wooden blocks as risers, each placed symmetrically. Mount slotted angle brackets on the risers to hold the pencil armature later. Then, add 2 regular angle brackets at calculated points and secure strong magnets to them. These will create the magnetic field essential for the motor effect. Install 2 electrically conductive screws into the base away from the magnets. These will serve as power terminals. Strip the ends of 2 rigid copper wires and wrap them around the screws. Align and tape the wires to the wooden board so they point straight toward the slotted angle brackets. These will carry current from the power supply to the rotating armature. Carefully place the pencil's sharpened ends into the slots of the angle brackets, aligning the coil with the magnets. Spin the armature by hand to check it moves freely. Now, connect the power supply to the terminal screws using alligator clips. Once switched on at 10 to 12 volts, the electrical current flows. The magnetic field supplied by the magnets interacts with the magnetic field supplied by the continuous current within the coil, creating torque and thereby rotational motion. This is where the motor effect will cause the armature to rotate, converting supplied electrical energy into mechanical energy. This is the completed armature of the DC motor, the rotating component that carries electrical current through the copper wire. As it spins, it interacts with the surrounding magnetic field from the magnets to generate torque and mechanical motion. This is the assembled stator, the stationary part of the motor. It forms the structural base, holding essential components such as the magnets, brackets, and electrical contacts in fixed positions to support the armature's rotation. This is the fully assembled DC motor, combining the armature, stator, and power supply. Crucial connections such as the alligator clips, electrically conductive screws, rigid copper wires, aluminium foil, and copper coil enable a complete electrical circuit. When powered, the electrical current flows through the cables, screws, rigid copper wires, aluminium foil, and then the copper coil, interacting with the magnetic field supplied by the magnets, which generates torque and initiates rotation, thus successfully converting electrical energy into mechanical energy through the motor effect. This is the DC motor in action, rotating at a relatively quick RPM due to sufficient power and torque. AC generators. Underlying physical concept. Operates based on electromagnetic induction. A magnetic field rotating within a stationary coil induces an alternating current in the coil. The direction of current alternates within the magnetic field's motion. DC generators. Underlying physical concept. Based on electromagnetic induction such as AC generators, but includes a commutator to rectify the alternating current inside the coil to direct current. The output is unidirectional. Photocells. Underlying physical concept. Based on the photovoltaic effect. Light in photons strikes a semiconductor junction, freeing electrons and generating a direct current through an external circuit. AC generators. Energy production method. Primarily turbine driven, used in power plants where turbines are powered by steam, from fossil fuels, nuclear or solar thermal, wind, or hydropower. Mechanical motion is converted into AC electricity. DC generators. Energy production method. Historically used with small-scale engines, now mostly replaced by AC generators plus rectifiers. Still used in specific applications such as battery charging, lab equipment, and DC motor supply. Photocells. Energy production method. Most commonly in photovoltaic PV panels made of silicon, arranged in arrays from larger power output. No moving parts. Converts sunlight directly into DC electricity. AC generators. Energy conversion efficiency. Highly efficient energy conversion. Large AC generators and power plants can reach 95% efficiency. The generator's internal conversion losses are minimal, but total system efficiency depends on the turbine or prime mover. DC generators. Energy conversion efficiency. Slightly less efficient than AC generators due to brush and commutator losses. Still effective in direct DC supply applications, with efficiencies typically around 85 to 90%. Photocells. Energy conversion efficiency. Commercial panels typically achieve 15 to 22% efficiency. Advanced lab cells, multi-junction, perovskites reach up to 47.6% efficiency. Performance varies with sunlight, angle, temperature, and shading. AC generators. Benefits. Can produce continuous, reliable power on demand. High scalability, mature infrastructure, and well-established technology. Excellent efficiency, and compatible with national power grids. DC generators. Benefits. Provides direct DC output without requiring rectification. Useful in systems requiring DC, such as electroplating, older electric locomotives, or experimental setups. Photocells. Benefits. Silent, clean energy production. Low maintenance. Long lifespan, 25 plus years. Modular and scalable. Ideal for distributed and off-grid power. No fuel cost or emissions during operation. AC generators. Drawbacks. Dependent on mechanical motion from turbines or engines, often powered by fossil fuels leading to pollution and emissions. Require maintenance due to moving parts and may have noise and vibration issues. DC generators. Drawbacks. Wear on brushes and commutators require maintenance, prone to sparking, less commonly used today due to simpler and more robust AC generators with rectifiers. Photocells. Drawbacks. Intermittent. Only works with sunlight, requires large area, low efficiency. Manufacturing involves energy and sometimes toxic materials. End-of-life recycling is still under development. AC generators. Societal and environmental impact. Enabled widespread electrification, industrialization, and economic growth. However, fossil-fueled AC generators contribute to significant CO2 emissions and environmental degradation if not driven by renewable sources. DC generators. Societal and environmental impact. Similar to AC generators, but more limited in modern use. Their use has declined with the rise of AC-dominated infrastructure, still useful in niche applications requiring pure DC output. Photocells. Societal and environmental impact. Extremely positive impact when replacing fossil fuels, reduces CO2 emissions and water usage, empowers remote communities, and decentralizes energy production. Some environmental impact in manufacturing and land use is present. AC generators operate under Faraday's law of electromagnetic induction, converting mechanical rotation into alternating current electricity. Their design, a rotating magnetic field within stationary windings, makes them efficient, scalable, and vital for centralized power systems. They are indispensable to national electricity grids, with modern power plants depending on them to generate large-scale power at up to 95% efficiency. A key strength is their compatibility with transformers, allowing voltage adjustment for efficient long-distance transmission. Their mechanical simplicity further contributes to their role as the foundation of a global electricity supply. Their benefits include reliability, high power output, and synchronization across grids for stable distribution. Multiple generators can operate simultaneously, enhancing grid resilience. However, AC generators don't produce energy independently. They rely on mechanical inputs, often powered by fossil fuels, which link them to emissions, environmental degradation, and climate change. The turbines commonly used, coal or gas-powered, emit greenhouse gases, yet the generator itself is not inherently polluting. When driven by renewable sources such as hydro, wind, or other motion-based systems, AC generators enable high efficiency, zero emission generation. Their dependence on frequency regulation, inability to directly supply DC current, and safety concerns from high voltage are notable drawbacks. Societally, AC generators revolutionized 20th century life, enabling widespread electrification of homes, industries, and cities. Despite this, their reliance on fossil fuels has left a significant environmental legacy. Although renewables now power many, fossil fuel turbines still dominate globally. The compatibility with clean energy sources positions them as a key to a low-carbon future. Thus, while historically tied to emissions, AC generators remain essential to reliable power supply and, when integrated with sustainable sources, are capable of supporting climate goals. DC generators function similarly to AC generators but use a commutator to produce unidirectional current. Historically central to early electric systems, they've since been replaced in large-scale applications by AC technology. Today, their utility is mostly confined to niche roles such as small-scale battery charging or electroplating, where direct current is necessary. They offer native DC output beneficial in specific contexts but suffer from several limitations. Mechanical commutation causes sparking, wear, and high maintenance. Efficiency is lower than that of AC generators, and thermal constraints limit their viability for high power use. Furthermore, DC voltage cannot be easily transformed, making it inefficient for long distance transmission. These constraints severely limit scalability and modern applicability. Societally, DC generators played a pivotal role in the early days of electrification but quickly fell out of favor. Their current use is largely isolated and diminishing, with AC systems and solid-state rectifiers now fulfilling their former roles. Environmentally, the impact is minor due to limited deployment. However, when powered by combustion engines, they still contribute to local pollution. Notably, DC generators can also use clean inputs like pedal-powered systems or micro-hydro setups, enabling low-carbon electricity in off-grid or humanitarian scenarios. While such applications remain uncommon, they demonstrate the potential for legacy technology in sustainability-focused context. Photovoltaic cells convert sunlight directly into direct current electricity via the photovoltaic effect in semiconductors, but passing mechanical conversion. As a clean renewable technology, they're increasingly valuable for sustainable energy generation. While typical efficiencies range from 15 to 22%, the abundance and free availability of sunlight, along with minimal operating costs, enhance their appeal. Photocells offer many advantages. The lack of moving parts reduces maintenance and ensures long operational lifespans. Modular solar panels allow for flexible deployment from rooftops to utility-scale farms. Technological innovations like bifacial and tandem perovskite cells are steadily increasing efficiency and lowering costs. Yet, limitations persist, mainly intermittency, as output fluctuates with sunlight availability. Reliable integration requires energy storage or grid support. Additionally, the environmental cost of manufacturing, including the use of energy and some hazardous materials, raises concerns over panel production and disposal. Photocells have had a growing societal impact by decentralizing energy access. They are especially transformative in remote or underserved areas where grid extension is impractical. Solar systems empower communities, reduce electricity costs, and cut fossil fuel dependence. Environmentally, solar panels generate electricity without emissions or water consumption during use, making them a powerful tool in climate mitigation. While challenges remain in recycling and resource sourcing, they are being addressed through innovation and policy. A critical comparison and contrast of energy production methods must consider not only efficiency and reliability, but also sustainability, societal impact, and long-term viability. AC generators currently dominate due to their scalability, maturity, and integration with existing grid systems. They provide consistent, bulk electricity, and when powered by renewables can align with carbon-neutral goals. These generators, by contrast, are largely outdated. Though once essential, they are now unsuitable for most modern needs due to technical limitations and inefficiency. The few remaining applications are in off-grid context, where they can still offer low-carbon solutions when driven by sustainable inputs. Photocells, meanwhile, offer a distinct and promising alternative. While less efficient on a per-unit basis and subject to sunlight variability, they generate clean electricity with minimal operational impact. As battery technology and smart grids evolve, the challenges of intermittency are diminishing. Solar technology also maintains one of the lowest environmental footprints across its life cycle and is crucial for decarbonization efforts worldwide. In conclusion, AC generators remain vital for today's energy infrastructure and can evolve into climate-compatible assets. Photocells, however, represent the most forward-looking solution. Their adaptability, affordability, and sustainability place them at the forefront of energy transition. A hybrid model, solar power generation supported by renewable-driven AC grids, offer the most effective and responsible path forward. Meanwhile, DC generators serve primarily as legacy technology with limited, though occasionally valuable, niche roles.